Welcome to Chapter 8, Further Applications of Integration. So we're going to overview in this video the chapter and the objectives. This is a new unit. We're now working with more interesting applications of integration, and so we're going to be expected to use the full range of our integration techniques that we've developed so far. To motivate the ideas and the cool things that we're going to explore in this chapter, we're going to talk about the center of mass briefly. Okay, so what center of mass means is if you have some object, for instance, a simple example that we can think of is some uniform plank of some thickness. So if we think about it as a one-dimensional object that's uniformly, it's got uniform mass. So in other words, the lines that I'm drawing here, they're not representative of anything other than if you could see inside, it would look roughly the same density all the way through. Then from experience, we know that if you just take the middle point of that that segment, that rod, then that's going to be the center point, the hinge point. And so if we generalize that idea of a hinge point to something that would work in not just a one-dimensional object, but two-dimensional, three-dimensional, then what we're talking about is the notion of center of mass. So for this one-dimensional object, the center of mass is a point somewhere in the object's area where it can rotate freely about that point. So there would be perfectly balanced. But what if we had something more complicated, right? What if we had something like, for instance, if we had a semicircle, well, that's not a semicircle. Whoops. Let me just go ahead and free draw this. Oops, okay. Pretend that's a semicircle, sorry. If we had the semicircle, right, and if it happens to be uniformly distributed, right, so it's the same thickness throughout, or sorry, the same density throughout, where would the center of mass be? So we would expect that, again, if it's symmetric about both sides, right, so let's say this is A, this is B, right, and if we think about it as occurring on a axis, right, with X and Y coordinates, then we would expect that if it's uniform, then that center mass is somewhere in the middle here, because both sides of the, on either side of the y-axis will contribute the same amount of mass. And so, but how do we verify this? It turns out that if we generalize the idea of center of mass to something that's continuous and distributed like this, then we discover that the center of mass is given by the points x bar comma y bar, where x bar is the x coordinate that gives the location given by the integral from a to b of x f of x dx over the integral of a from a to b of f of x dx, where f is the function that determines the shape of this particular object or solid. And similarly, we do the same for the so for the y coordinate of the center of mass, it's given by this expression. And we'll derive how this comes about. And so what you should think about is this is defined by y equals f of x. And when it can be expressed in this form, right, then this is the formula for the center of mass. We are going to do all sorts of generalizations of this and discover how to tackle the unique different geometries. So again, we're returning to the idea of, we're going to combine our initial knowledge of geometry, algebra, combine some of the calculus techniques we've already discovered to be able to fully express how to handle a center of mass calculation for different objects, different densities as well, okay? Because if the density changes, then this also changes, but we'll talk about that later. In any case, this chapter has 5 sections. We'll cover it in roughly 2 weeks. Just be aware that it is going to require some background knowledge, and I'm happy to provide that background knowledge whenever necessary. We're going to see